about this matrix, where does, so assuming that we have a matrix A, which when it is diagonalized, it looks like this, which means that the eigenvalues of this matrix A, they are 2, 3, 2, 1, 3, okay? Then we have another matrix B, and the diagonalized version is like this, which means that 1/10, 3/10, and 4/10 of are the eigenvalues of B. So what can you say? What would happen if n is large? Okay. Now we can say like this: if n goes to infinity, or if n is much larger than 1. What can happen with matrix A to the power n? What can you say here? And what can happen with the matrix B to the power n? Now, regarding the matrix A to the power n, we can simply say, or easily say, that this will diverge. And B, it will converge, okay? So, but where A is going to diverge, the A, it is going to diverge to a specific value, which we don't know where it is. It's going to diverge to infinity. And B to the power n, it will converge to a very well-known point, which is 0, okay? Because 0.1 n, so this is like 1/10 to the power n, this is 1 divided by 10 to the power n, and exponential, a number to the power n, this is an exponential increase. So they are very fast converge to 0 or very fast diverge to infinity. So, or let me also ask you, we can also look at the following problem. Let's assume that this is 0.1, 0.3, and let's make this 1. So if we make this 1, the B to the power n, it will still converge to some value, but it will never diverge. Okay? This is an important problem that you, at this stage of your studies, you should always keep in mind that, okay, so even from the issue, from the course of linear algebra, you can carefully analyze whether a system can converge to some specific values or diverge to some unexpected value, such as infinity. Okay, so we should keep this in mind because now we are finding eigenvalues, and it looks like for real life problems, we might like more the problems that can be described as a matrix B. Okay, because for real life problems, we don't have too many quantities which exponentially increase, or if they do, that means that we'll lose them very soon. So if let's say, if the cost for a system increases exponentially, then you don't deal with it at all, the cost or the price. Or if let's say, or if the need is increasing exponentially, what do you do for that? You do nothing. If you need a specific quantity or some amount, let's say that you need an exponentially increasing number of computers to do a very complex calculation. Nobody can provide to us an infinite number of computers which can exponentially increase. So let's see another example. And in this problem, I'm going to write this one immediately using the matrix notation. Let's assume we have xt plus 1, yt plus 1, and zt plus 1. These are three variables, which unfortunately, they are coupled. What do we understand with coupling of three variables? The coupling of three variables is such that if we write down the matrix 3 by 3, we have a lot of off-diagonal terms. So if we say that this is a coupled system, we can say that, or we can look at these numbers. This is 13 minus 8, 2, 7, 17, and minus 2. So we look at the off-diagonal terms. So this is our 3 by 3 matrix. And it does not look good at all, because these are non-zero. Okay? So apparently, this is the problem we are offered to solve. And approaching to the problem critically, this is the first thing that we should notice. But then let's look at the diagonal terms. Apparently they are non-zero, and here we get a minus 9. And this is the mixing matrix, or the we can put whatever names to this. And here we have the variables, which is xt, yt, zt. And then, so the first thing we observe is that, okay, A is not diagonal. What is that? So this is given. What should we consider next? Next, we should immediately try to identify what is the diagonal matrix, which in fact, the diagonal matrix, it will be a matrix composed of lambda 1, lambda 2, lambda 3, and all zeros. We have to determine what is the matrix P and what is the matrix P inverse. Okay, so this is how we should approach to the problem. Now, at this stage, it looks like we have to identify. Well, we can write. We have a standard basis here, which is 6, 13 minus 8, 2, 5 minus 2, 2, 5 minus 2, 7, 17 minus 9. Okay, so here we have the standard basis. And we want to construct the basis, the best basis, which can help us to solve this problem more correctly. If we work carefully, well, if we work carefully for the diagonalization of the matrix A, we will figure out that the eigenvalues of matrix A, they will be minus 2, 1, 3. So then this matrix A in the new basis B, and this is the standard basis, the matrix A, this will be represented as minus 2, 3, 1, minus 2, 0, 0, 0, 1, 0, 0, 0, 3. So this is in the new domain. This is how A will look like. Okay, and then the question that can come up from this type of formulation are the following. So given an x0, find what is xt. Okay, so this is, let's say, so traditionally we will be given these. We will be given a matrix A, which gives us the mixing matrix between the three variables. We'll be given an x0, and then the question will be to find xt. So it looks like the problem, given these, find these. Okay. So we have to determine all of these. With a little bit of work, we can easily identify that the D will look like this. We did the first step. Then, given these eigenvalues, minus 2, 1, 3, we have to determine what is the matrix P. And we can write the matrix P immediately. And P is equal to, so we have to write in the first column, we have to write the eigenvector of the first eigenvalue. So this minus 2 corresponds to an eigenvector which is 1, 0, 1, 1, 0, 1, minus 1, 1, 1, 1, 1, 2. Okay, so this is the matrix P. The matrix P inverse is equal to minus 1, minus 1, 1, minus 3, minus 1, 2, 2, 1, minus 1, 2, 1, minus 1. So, okay, so we're good. It looks like we know now that we know the P, we can easily determine, so we know by now, so we can figure out how. So we have A, we have B, but these P's, what will be useful a lot will be how we can transform these initial conditions in A, how they look like in the new domain here. Okay, so that's why what we are going to use them for. So for a moment, let's assume that x0, the initial value in this domain, is equal to 1, 1, 0. Okay? And the question is, let's find xt. I might need this space. So this is a given. We want to find what is this. Okay. Now, if this is, so we're given this x0, and how can we find the xt? The first approach will be the following. We can say, okay, so this is what we are asked. We say, what is xt is equal to, this is equal to a times t plus 1, a xt. Then this is equal to a to the power t times x0. Okay, so this is how we move forward. And then a to the power t times x0, this is equal to the matrix P times d to the power, let's write the notation t also, d to the power t times p inverse times x0. Okay, so this will be what we will need to use step by step. Then, then in here, so we can continue. We can write here the p. This is 1, 0, 1, minus 1, 1, 1, 1, 1, 2. Then d to the power t, this is equal to minus 2 to the power t, 0, 0, 0, 1, 0, 0, 0, 3 to the power t. And then we multiply it also with p inverse, which is minus 1, minus 1, 1, minus 3, 1, minus 1, 2, 1, minus 1. Okay, then we have to multiply these also with the initial condition, which is 1, 1, 0, 1, 1, 0. And then we need to do these calculations. So this is the first approach, okay? This is what we need to do. Now, the second approach, it can be the following. So let's assume that in this new domain, we have a u0, which we don't know what it looks like. Okay, let's leave it like this. And then we can also have a problem, which can be here ut. What is ut? Now, and if we see here x0 and u0, so this is not finished yet. I think we can see this part of the board, so we can write the following. So let's write the major equations. You can see this part. We have this here, xt plus 1. This is equal to a times xt. Okay, that's one piece of important information. Then we have also, and this is also a to the power t times x0. Then we can write that any x is always equal to matrix P times u. So this is, what else can we write here? We can write also that ut plus 1 as a vector, this is equal to d times ut, okay? Or d to the power t times u0. Because, so let's write it here. So apparently we can say that ut to the power t plus 1, this is equal to the d to the power t times u0. So it looks like the problem, if we move this problem that we are trying to solve, as defined in here, given a and x0, this is equivalent. So if we change the basis, these values for x, y, and z, they will be such that the coordinates of u0, they will not interfere. So they will be decoupled. So in this case, what we can do is that, well, let me say it this way. So simply, this will be the solution. The only thing that we need to figure out is what is u0. How can we find u0? u0 as a vector, this should be equal to the p inverse times x0. Okay, and let's write this down. Let's find what is this. The p inverse times x0. P inverse is minus 1, minus 1, 1. minus 3, minus 1, 2, 2, 1, minus 1. We multiply this with the initial value, which was, so let's not forget, we're coming this way with P inverse, 1, 1, 0, 1, 1, 0. And this is going to be equal to minus 1, minus 3, this is minus 4. Then we have minus 1, minus 2, this is minus 2. And then we have 1 plus 2, this is 3. So it looks like the initial conditions in the standard basis, there are 1, 1, 0. But in the new basis, it's minus 4, minus 2, 3. Minus 4, minus 2, and 3. Okay? So then, let's look at how the problem looks like in here. So, this is equal to, what is d? D is minus 2 to the power t. This is 0, 0, 0, 1, 0, 0, 0, 3 to the power t, times, what are the values? Times the initial condition, which is minus 4, minus 2, 3. Minus 4, minus 2, 3. Okay? And so this is a matrix which is 3 by 3. This is a matrix, a vector, which is 3 by 1. And the answer, it will simply be written as minus 4 times minus 2 to the power t. So this is minus 4 times minus 2 to the power t. And then this is equal to minus 2. So apparently, this will be a constant value. And then we have also 3 times 3 to the power t. 3 times 3 to the power t. So we found it. This is the answer, okay? Now, this is the answer, but this is the answer in this basis. So it looks like we can write this one in here. We can say that ut at any case, in any case, will be as such. Let's write this minus 4 minus 2 to the power t minus 2, 3 times 3 to the power t. Okay, we solved the problem. We didn't spend much time at all, okay? Because all we needed to know, we needed to know what is the initial condition in this new basis. And this is the answer. But now that we know this answer, we need to see how does this project onto the initial basis. So we have not found this yet. We can find it here, but it looks like it's going to include some a lot of calculations. But now that we know this, how can we? So we were here. We knew x0. We found u0 by multiplying with p inverse. So this is, let me write this one. This is p inverse times x0. We found the u0. Now we have the ut, and because this is the ut. And now we're going to do the other. We're going to say p times ut will be equal to xt. Okay, so this is how we move from one side to the other. And here, let's see the answer, which is going to be xt. This is equal to p 101, 101 minus 1, 1, 1, 1, 1, 2. And this all is multiplied with this minus 4 minus 2 to the power t minus 2, 3 times 3 to the power t. And as an answer, this is a matrix 3 by 3 multiplied by a vector which is 3 by 1. So here we expect also a vector which is 3 by 1. Then in this case, these three terms that we see here, it looks like we have to get the first one minus the second plus the third. Okay? So the first one minus the second plus the third, we get the following. This is minus 4 times minus 2 to the power t minus the second, which means this is plus 2 plus 3. Let's try this for a moment. 3 to the power t plus 1. This is 3 by 1 vector. The second vector is we add up the two terms, the second and the third. So this is equal to minus 2 plus 3 to the power t plus 1. The third term for x, this is the summation of the first two plus twice the third one. So this would be minus 4 minus 2 to the power t minus 2 plus 2 times 3 to the power t plus 1. Okay. So now this expression, if we are to write down here the xt, is going to look a little complex. I don't want to write it here for the moment. But this whole, let me take this away. Let's write this. Let's leave it like this. So the answer, the xt or the solution is here. So how did we find this? The short way, it was that we just needed to find what is u0 in this domain. We multiplied with d to the power t. It was easy because this was a diagonal one. We found this solution. Then this solution, we need to project it back into the standard basis, and we find this. Okay. So, and again, how do we do it otherwise? Otherwise, we just need to, so this solution that we found here, so this part that you see here, this is the solution. We're done. Otherwise, we'll do the following. We'll multiply this matrix P with this, and let's see what we obtain. So this is 1 with a second. So this is the first row times this column. This is minus 2 to the power t. And then we multiply the first row with the second column. We get minus 1. The first row with the third column, we get 3 to the power t. Then the second row with the first column, we get 0. The second row with the second column, we get just 1. Then this with this, what is this? 3 to the power t, right? This is 3 to the power t. And then we multiply the third row with the first column, we get minus 2 to the power t. Here we get 1, and this we get 2 times 3 to the power t. Then we multiply this with what we have here. Okay, this is the vector. So let's write the answer here easily. So we multiply the first row with the first column here. So, and this here, we're going to get a minus sign. So this is minus, what is it? Sorry, this is minus 2 to the power t. This is all because the first row with, no, sorry, I have to multiply this row with this column because I'm just saving my own time, but sometimes saving time makes things more difficult, or I can easily be confused. So I just rewrote it in here. So we get minus 1 times minus 2 to the power t plus 1 plus 3 to the power t plus 3 to the power t. Then we have to obtain the second term, which is going to be minus 2 to the power t. We multiply this whole thing with this. Okay, so this will be minus 3, which is this minus 3 times minus 2 to the power t, minus 2 to the power t, plus 1, because minus 1 with this minus 1 is plus 1, plus 2 to the power 3t. Okay, then we have the third term, which is the first row with the third column, and we have to look carefully. This is 2 times minus 2 to the power t, minus 1, minus 3 to the power t, minus 3 to the power t. Okay, we got done with this one, and in the end, we will have to multiply with 1, 1, 0. Okay, then again, let's multiply the second row with the first column. Second row, this is going to be just minus 1 plus 3 to the power t Then we multiply the second row with the second column. This is minus 1 plus 2 to the power 3t plus 2 to the power 3t. And correct me if I make any mistake, okay? So then we have here 2 times minus 2 to the power t minus 2 to the power t plus 1, because there's this 1 and this 1, minus 2 to the power minus 2 times 3 to the power t. Again, here we're going to have a minus 1 minus 2 to the power t minus 1 plus 2 times 3 to the power t. Then we have minus 3 times minus 2 to the power t minus 1 plus 4 times 3 to the power t. Finally, we get 2 times minus 2 to the power t. Who can help me here? Plus 1 minus 2. You'll say that, okay, you'll say that no one is going to help you because you messed up it yourself by using the matrix A to the power t. You better, it could have been an easier solution, which is seen down here. Then, finally, we have to put together this matrix, which is here 3 by 3. So we have this 3 by 3 matrix, which has some volume in itself. It's not a small one. We have to multiply this 3 by 3 matrix with this 3 by 1 vector. And
Professor, I think it's an error because row 2 times column 3.
Yes.
It's 1 minus 3 to the power t.
Let's see. So you see row 2 with column 3, right?
Yes.
So row 2, column 3 is this number. So we are saying that this is wrong?
Yes.
Okay, let's check this one. So we get, yeah, that's a mistake, right? Because we have a 0 here. Wait, no.
You have done twice row 3 times column 3.
So you mean this is extra?
Yes. It's 1 minus 3 to the power t.
That is correct, yes. Thank you for letting me know. Yes, it would be, but the rest is, it's good. What about, is this correct then? This is minus 1. Oh, this is good. Okay. Thanks for noticing this. It looks like the second row, it's elegant row, because this is how it is. Now, what remains for us is that we need to do one more calculation, which is the following. The result here, it will be the summation of the first two columns, okay? Because we know that if we multiply, so if you have a matrix A times another vector, the result, it is going to be in the column space, okay? So we remember the column space. So the result is always how the first column, the second and third are related, and here it looks like the answer, it will be the first column plus the second column. Because each time we're going to multiply these, we have here 1, 1, 0. So it will be this number times 1, plus this number times 1, plus this number times 3. And probably it is best if we, because this might be a little confusing, so this is the second term, okay? In order to clarify them or to make it a little more visible, so these are all, they all represent single terms, right? So this is a 3 by 3 matrix, and here the numbers are. I tried to draw them as best as I could, and but this might make this a little more obvious. So here we have all of these numbers, so it looks like the first term, it will be, we add this one, and let's see if we have found the right answer. So here we have minus 2 to the power t, this is minus 3, minus 1, this is minus 4. Now, I'm just comparing this result here with this one, so it looks like, so we're just, forget about this one, okay? So if you want to forget this, let me stay right here. So I have a purpose for staying here, a very strong one. And then, so let's add up these two terms. We get minus 2 to the power t, minus 1, that's minus 4. That's good, we got that. This is 1 plus 1, this is 2. There is this 2. And we have 3 to the power t, 3 to the power t. 1 plus 2 is 3, so that's correct. This is 3 to the power t plus 1. Okay, so we got this right. Then the second term, we add this number and this number, we get minus 2, which is this minus 2 here. 3t, we have 2 3t and 1 3t, this is 3 times to the power t plus 1, that's also correct. And then we have also minus 2 to the power t, this is minus 3 minus 1, this is minus 4, this is correct. Minus 1, this is minus 2. And then we have also 4 plus 2, this is 6, but 6 is equal to 2 plus 3, so this is also correct, okay? So it looks like we found the same answer using two different methods. And what we try to promote today is that this is relatively simpler, but this remains for you to judge. And it is also less confusing because here we do a lot of, you can also count the meter squares or the foot squares that you spend on the whiteboard, and then you can judge which one is simpler. Okay, so another example that we can try to convince or to see another example is the following. Let's think for a moment. So this is xt, we found it, we ended up being in the same way, but let's assume, let's say, what is u5? Or let's do u4. What is u4? u4 is going to be equal to minus 2 to the power 4. This is 4 times 4, 16. 16 times minus 4, 32 minus 64. Okay, this is minus 64. Minus 2, and this is 3 to the power 4. This is 9 times 9, 81. 81 times 3. What is 81 times 3? This is 243. 243. You can correct me if I'm wrong. So this is u4. So let's assume that we can write this one here. This is minus 64, minus 2, 243. So this is a vector which is generated after 4 instances. So we have 4 subsequent values, and this is what we get. And the question is, if this is u4, what is x4? How can we find x4? In order to get x4, how can we go from this domain to this domain? We have to multiply by p, right? So if you multiply by the matrix p, let me write this right here. But that's because it will be easier for me to do the calculation in here. So we multiply the matrix p. Let me put this p inverse a little like this. And we have to add here. Let's multiply with these respective values. Minus 64, minus 2, and 243. So what is x4? This is 1 minus 64 plus 2. This is minus 62 plus 243. This makes this 181. So this is 181. Then we have minus 2 plus 243. This is 241. And then we have minus 64, minus 2, minus 66, plus 2 times, this is 486. 486 minus 66, it's 420. 420, is it 420? Can you check this? So again, this is 486. It's 420. Yeah, that's correct. Okay. So this is how we can make use of the. So what we did here, we got the UT, we found the U4. then we can easily find the x4 by multiplying or by using. So here we just multiply with this matrix P, this, and this is what we found. Okay. Now, do you have any question for what we have on the board? Okay, if you have no question, we can take another break.